There are so many dark clouds in modern physics. Let's go back to classic physics of early 1900s and ask classic questions for elemental particles. Maybe it is time to revisit quantum mechanics and theory of general relativity. This is our new direction of physics.
Today we're going to continue our new direction of physics videos. This is video number 8. We're going to be starting a new self-interacting field theory, how it's applied to the microworld. In the last video, we talked about how the self-interacting field theory can trap the field in the 3-dimension, 2-dimension, 1-dimension, the space, okay? 3-dimensional space, we see that it has boundary, okay? It has a boundary, okay? Okay, so the 2D, that's the dark matter, okay? We think it's quantum mechanics, okay? So that's in the last video we talked about. Especially if the 1D field it's trapped, the field cannot go farther away because the force equal constant, so the potential energy equals constant times R. That means the further away, the more energy you require. So in the end, you don't have infinite amount of energy. That's why once you have into a 1D trapping, the field has to come back, okay? So that means the 1D trapping, the field is attached to the parent particles. It's the virtual particles, it's the 1D trapping. That's why we would like to try to explain this in our microworld. Okay, so what does microworld look like if all the elemental particles are made of a self-interacting field, are all trapped together by self-interacting field? We had question number 1 and number 2 of this series of videos we talked about. So the first one, it's about the gravitation. Second one, it's also about gravitation. Now we're getting into the question number 3. So this electron, photon, or quark has internal structures. The current mainstream physics say no, okay? But what force binding the electron is rotating, okay? It's spinning pretty fast, okay? It's spinning, okay? How do we bind the electrons, okay, together? Because all the charges of the electron, they're repulsive, and also they're rotating, both rotation and spinning. They are the force to go apart. It's repulsive. So we need some kind of field to bind them together, okay? So the question number 5 we asked in the first video, can strong interaction reach out to macro scale? The current physics say quark is confined. But what I'm talking about, the interaction of the strong interaction can reach to the macro scale, okay? What we have is a mediator of the interaction. It's a result of field interaction. Field is a mediator. We don't need mediating particles, okay? If we assume that all the elemental particles are made of self-interacting field, then we would like to study the field properties. So there will be a self-interacting, I would like to call self-interacting strong interaction, which binding the particles together, okay? The nuclei, the quarks, and even the photon, okay? That's what we are trying to propose. Let's see, because we have the self-interacting field theory now, okay? We have the self-interacting Newton's law of gravity, self-interaction Newton's law of gravitation. We have a field equations, Newton's law of gravitation, okay? We have this theory, okay? We would like to apply this kind of theory to the elementary particles, to the microworld, to see what it look like, okay? So the foundation of quantum mechanics, I put it into 6 parts. We can show that the self-interacting field and quantum potentials has the same format, okay? So why the elementary particles spin half, not spin 1, okay? Okay. The Pauli exclusive principles, the Einstein's quantum assumptions, sometimes most of the familiar, a lot of physicists wrote like that, okay? Because H equals H bar times 2 pi, okay? Or H bar equals H divided by 2 pi, okay? But F equals H, okay, equals 2 pi V, okay? So, yeah, if we replay that, that's exactly the same, okay? We will rewrite the uncertainty principle, okay, to see what that means, okay? We can write it into like a Newton's law of gravitation, okay? This is the potential, the field equations. This is Newton's law, F equals G m1, m2 divided by r squared. So the most simple quantum mechanics, it's a particle trapped in one-dimension box, okay? We will do a computer modeling to see what it looks like, okay? What do we mean? It's a self-interacting field theory applied to the microworld, okay? If we apply this to the microworld, then we can explain all this. So this is, especially when I derived this, I was so excited, okay? I was like, Jesus, this is good. I'm on something right, okay? Something maybe have some important meaning. So we know that the quantum potential, self-interacting Newton's law of gravitation, or the Newton's law of gravity as SI field, okay? That's the equation, what look like, okay? So if I close to 1, in the weak field limit, it goes like that. The quantum mechanic potential, quantum potential, okay, quantum potential, it's like that. Because the quantum energy, they already defined in the field equation, they already defined S equals normal S divided by h bar. That's why they already have an energy scale of h bar in there. So the strings will be h bar times h bar over m. That's already predefined in other parameters. This is why it's h squared. Yeah. So it's clear that quantum potential is a self-interacting field. If we treat that as h bar over m, okay, divided by 4g m. If we do something like that, that's 10 to the 39th. Okay, that's a scale. So what gravitation, it's proportionate to g and m. Okay, and the quantum potential, it's h bar over m. So these two ratios, it's 10 to the 39. From the forms of the field equations or the quantum potential, we see that they have the same format, except the strains are different. We keep seeing the 10 to the 39th, this scale. We'll come back to this scale. That's Dirac, not number hypothesis, Dirac, okay, large number hypothesis, okay. Okay, we've seen this before because we use this number, replace the gravitation constant. We use Hawking theory to calculate the nuclear mass, pion mass. This is why this scale is very important. Now we see the quantum mechanics also have the same scale. But then people can say, hey, Q, you're using gravitational constant and strong interaction constant. Now you are talk about quantum mechanics, we will see in the future that quantum mechanics, it's a self-interacting strong interaction. They are the same amplitude. The length of the quantum potential, the strength of the quantum potential is that, okay? So we did that, we already did that in the previous presentation. Why the elemental particle is only spin half or up and down. All particles, all elemental particles spin up and down. Electrons, whatever you talk about. Why is that? Because as we know that in the self-interacting field theory we're proposing, all the field being trapped. Now if the particle is spinning, you can only interact from the equator because that's where the field can escape. From the polar, there is no escape because you don't have the rotation to help you. The rotation is helping on the equator. If you have some field escape from half of the equator, like 45 degrees over here, but then because of the field can be bent, because you have energy being spread on the equator. Field on the equator will bend anything you escaped from a little bit higher than the equator, they're going to bend here. So all the field will be bent here, like that. This is why you can only interact from the equator. That means if you touch the field to interact, because if there's no field, no interaction. Any field line escaped from anywhere non-equator will be bent, focused onto the equator. This is why field can only escape and interact from the equator. So you can't have the particle moving like that, okay? That means when the particle at the equator go like that, you can interact from the equator. But your spin is defined by right hand, the way of determining. But the trouble is that where the interaction only from the equator, so you can only spin up and down. You cannot push the particle from the top and bottom. The elemental particle only interact from the equator region. This is why they have only two spins, up or down. So the current physics say, okay, that's spin half. Because spin half, you have positive half, okay, minus half. So this is what it means, spin up and spin down, numerically. That's why they claim it's spin half. What, based on the self-interacting field theory, the elemental particle, it's not spin half. Okay, but spin one. But lost the zero component, okay? Why I'm saying that? Because the elemental particle, the gyromagnetic ratio, that means the gyro is the physical movement. The magnetic field is the charge, the magnetic moment. So suppose you have a physical movement, angular momentum. So if you have, okay, the electron rotate about the nuclei, you have the angular momentum. So the magnetic moment produced, it's equals 1, okay? That means gyromagnetic ratio is 1. But our elemental particle gyromagnetic ratio is 2. If we have its spin 1 but lost the zero component, then the gyromagnetic ratio is also 1. Philosophically, we think the gyromagnetic ratio should be 1 instead of 2, because the same charge, the same movement, everything is supposed to be the same. Then they produce the same moment, magnetic moment, okay? But the elemental particle is 2 because we lost the spin 0, okay? Because we can only spin up and down. That's why physicists would like to say that's spin half. But the true spin is spin 1. So the Pauli exclusion principle, okay? When the elementary particle only spin up and spin down, okay? So if we see the field movement, we see that, okay? So if you have the spin up and spin up, in this region we see that we have the field move in this direction and field move in this direction, then they collide over here. Okay, they're opposite direction, then they are colliding. So the force will be colliding, so the particle has to move away. Okay, but you see that if we have a spin up and a spin down, okay, it's like that. Okay, when they touch, they're moving in the same direction. So they collaborate, okay? Because they don't collide. This, they collide, they collaborate. They can pass energy, you can give to me, I can give to you. It's as long as the energy is the same, so they are fine. So when you have spin up and spin down, they go together, they're fine. When you have another spin up come in, then they will collide with the spin up. If you have another spin down, especially if they're rotating, they're in an orbit, they're going to see each other, especially when they're rotating, okay? So that means you can only have a spin up and spin down in the same orbit. That's Pauli exclusion principle, okay? So this is, I think it's most natural explanation of the Pauli exclusion principle. But in the current quantum mechanics, they just say, okay, that's a principle, okay? The microparticles, the elementary particle follow that, okay? But why? Now we give a reason, a physics reason, why they can only spin up and spin down in the same orbit. So in the next video, we're going to talk about Einstein's quantum energy assumption, okay? And also the gravitational property of uncertainty principles. And also we're going to talk about the 1D box of the elementary particle being trapped in 1D. We will see whether it has quantum properties. But we didn't use the quantum mathematics. We will only use the elementary physics we have, or high school physics we have. But we allow them to collide, to emitting energy, take it back, emitting more energy, so that the particle emitting energy on both directions. So we see that in the middle, they emitting on both directions. There will be more chance they're going to stay in the middle. Okay, but if you know some basic quantum mechanics, you know that the property of the elementary particle in the box, in the middle, they have same higher probability they're going to stay in the middle. Once you get to the closer to the right side, then they move to the left side. Once they go to the left side, they move on to the right side. So they're going back and forth. Okay, this is for the next video. Thank you.